All right. What's up, everybody? Welcome to Jupiter Brain. Today is round 2 with Dr. Teo. So we are super pumped. Supposed to have him on last week, but Dr. Teo's a busy man. So
Very busy. But yeah, so before this podcast started, I unintentionally asked him like some interesting questions.
Okay.
So would you like continue like explaining to like us why recently you got so interested in like quantum computing or quantum cryptography? Yeah.
All right, so I think the interest got developed from we had that ABET visit, and I met with some of the specifically the engineering physics advisor. And so for the past maybe 2 years, we've been able to we were struggling to offer quantum. So each time that we offer quantum, we don't meet that cutoff, so we need at least 5 students in order to offer the class. So we've always been getting like less than 5 students, so 2 students, 3 students, and so because of that, we've not been able to really like offer the course. But when we met with the evaluator, his suggestion was to, instead of focusing more on complicated stuff, solving complex differential equations for hydrogen atoms and things like that, why not do something that is applicable? So why not think along the lines of like quantum information systems? Because that's really like, if you think about computing, that's like the next generation. So computing is moving towards that area.
and it's in the zeitgeist right now. Everybody's talking about it.
Yeah. So with that, I was able to put together some ideas, and I created this, like a flyer which was sent out just to advertise the new approach. And so this time around we got about 8 students who enrolled in the course. So actually it could have been more, because I think I had maybe 3 or 4 electrical engineering students that they wanted to take the course.
The conflict, right?
Not conflict, but the flow chart. So engineering, electrical engineering, if you look at the flow chart, it doesn't allow students to take any
electives.
Oh, really?
Wow.
Right. So that was really a problem, because I had 4 students. These are students that really wanted, they wanted to learn about quantum computing. But for some reason,
And do you have to take modern physics before you take quantum, or?
So that's something that we're working on. In the past, modern was like a prerequisite for quantum, but now we're trying to relax that requirement, because, as I said, the emphasis is more on quantum computing. So basically, what you really need is linear algebra. So if you've taken any class in linear algebra, I think you should be good. So we're working on it. So in the future, it's going to be like a curriculum change, where we're going to make some adjustments on, henceforth, going forward from now, you don't really need modern. So we could say maybe modern or some advanced math, like maybe linear algebra or something. But you must have completed something, some advanced math. I don't know, maybe Calc 4 or some linear algebra.
Or DiffyQ.
Yes, or DiffyQ, right, something like that. Yeah, so I started teaching the course this semester, and so basically, if you think about quantum computing, the way the textbook does it is that it starts from like the foundation. So the foundation is to introduce what the qubit is, which is a kind of, I know you are not interested in superposition, but the qubit is some kind of like a superposed quantum state that way you can say that an electron spin could be either in the up or down state.
Yeah, we were just talking about the block sphere.
Actually, it's the block sphere.
Yeah, qubits and everything before, right before you got here.
Yeah, all the different gates, the Hadamard gate and all that.
That's basically what we've been doing. So we started with simple qubit systems, and then we introduced like basic quantum circuits, like the Schwarz circuit and things like that, CNOT, and then from there we started making some complicated circuits. But again, we've been working on implementing this using the IBM Qiskit.
Yeah.
So I have some projects where some students are working on developing. Again, I will not say very complicated code, but just something basic.
Yeah.
Can you pull up like Qiskit?
I'll pull it up and you can keep talking.
Yeah. So Qiskit, as a matter of fact, it has some really good tutorials.
I think it's like that.
Yeah, exactly. If you go there. And then I think if you go where it says get started, like right there,
yeah.
get started.
Wow.
Now you can scroll. Yeah, you can see those are some basic, and you can actually run some of those on the Jupyter Notebook.
Yeah, and then you can build circuits in
You
here,
can
right?
build some circuits. Yeah, you can build circuits and things like
Circuits
that.
and operators.
So, what do you think that UCO should have access to real-world like GPUs or quantum simulators? So not GPUs, quantum computers or quantum simulators, or do you think that we should have our own?
I would say from the beginning, if we can use something like
Just like a cloud one?
a cloud-based, because this is something that was still, I would say, was still like really at the beginning stages.
Yeah.
So we want to test it, make sure that we understand what is going on. Eventually, in the long run, we can even start to do some
Real circuits.
like some real circuits, even some experiments, because Dr. Tage has these ideas about like, quantum hardware.
Mm-hmm.
So how do you implement a qubit in the real life? Like, and these things are based on some kind of like, it's called engineered potential wells, where you can confine an atom within a region in space, right? So if you can confine that atom, maybe you can manipulate its spin and things like that. So eventually, I think we need to really like move, get more excited about some of these like, because I went to that conference in Denver, Colorado 2 weeks ago.
Wow.
Everything. So in the past, so part of the conference is called the exhibition. So exhibition is where you have like industries. They show some displays of cutting edge technologies and what they're doing. This time around, everything about the exhibition, so 100% of all the companies that participated is about quantum computing.
Wow.
Quantum circuits, quantum technology. So when I came back, I was really like, I was amazed by how much interest. And this is an international conference, right? So you have participants from all over the world.
Wow.
And everybody that took part in the exhibition, they displayed some of this like complex hardware that implements quantum algorithms and so on. So something that I'm working with my students, again, this is just for introduction. There is something called the quantum advantage.
Mm-hmm.
So the way that works is, how does the quantum system, so for example, if I have a problem that I'm trying to solve, right?
Mm-hmm.
I can solve this problem on the classical computer and take the same problem and try to implement it on the quantum computer. So what advantage do I get for using a quantum computer? So that's something that I feel like is very interesting to me, especially so my research is mostly electronic structure.
Mm-hmm. Oh, yeah.
And electronic structure is a very complicated problem to solve because you're dealing with different degrees of freedom of electrons, right, within a crystal.
Yeah.
So those electrons can move in completely random directions and so on. So there's been a lot of talk out there by researchers that it seems like quantum computers might be suitable to solving this type of problem, right? So it might be one of the areas where we can see quantum advantage. So what that means is that something that maybe you can solve at time t, using a classical system, maybe you can solve it using a quantum system by some, maybe t over something, t over 8, t over 16,
So they have
t over 20, something
see.
like that, right? So if you can cut down the computational time, that would be a significant, because t could mean, like right now, we have a project that I'm working with a student that is at Lehigh University in Pennsylvania. And we were just discussing yesterday about trying to get in touch with OU because we're trying to run some calculations on the OU system. And he was saying that one of the main problems that he's facing right now is the time. So the calculation is going to run because at Lehigh University they have like some constraints on the number of nodes that you need to use and the time that you need to allocate, and so it's a maximum of 3 days.
Really?
Yeah.
Wow.
And so what he does is that he will run this calculation, and then at the end of 3 days, when it times out, he has to go into the input and extract the current geometry. So the geometry is changing for each step, right?
Yeah.
So he would go to and extract the final geometry at the end of day 3. So copy that and put that in the new input file and then restart the calculation again. And so that's what he's been doing.
Yeah, which is a pain.
It's the pain, right?
Yeah.
So he said that for some of the calculations, it's taking weeks. Weeks, 2 weeks, and stuff like that. So,
Yeah, and I know, if I can remember right, Oscar's queue allows you to do, if I remember right, 12 days.
Okay.
I believe. And they even say, like, if you need longer,
Right.
message them, and they should be able to set you up something.
Yeah.
But yeah, that's one thing that I run into a lot too, is like, for one, sometimes you don't know how long your computation is going to take.
Yes.
And so you start off, okay, let's start off with 2 days,
Right.
because you don't want to also busy up the queue for other people as well.
Yeah.
And then so sometimes you end up you end up having to rerun it. So
Right.
so what I give advice, if I have any advice, is make sure you save checkpoints along the way so that you can do what the guy you're working with did, is basically take that last checkpoint and then have it as
Continue running.
input for continuing.
Yeah, so for some of the calculations that we do, I think when we're starting to run the calculations, we actually spend some time to estimate the time. Like, so we do what we call benchmark calculations, where you run the calculations for very simple systems.
Like toy models.
Like toy models. For example, let's say that I have there is something that is called a supercell. The way it works is that you take the unit cell and then you just multiply it in all 3 dimensions. So for example, let's say a supercell has 2 atoms, right? So if I scale that by a factor of 2 along the x, y, and z, that's 2 to the power of 8. So now instead of 2 atoms per unit cell, I'm having 2 to the power 8 times 2, which is 16 atoms per unit cell. So what we do is that we make these supercells, and then we run the calculations for each supercell, and then get a graph, and then we can feed the graph. See, is it increasing exponentially? So for example, if I run the calculation for a supercell that has 2 atoms, and it takes, let's say, 2 hours, right? And then maybe if I increase the number of atoms to 4, and it takes 4 hours, it tells me that maybe it's scaling like the square. So if I can get that relationship for simple systems, it gives me an idea how the calculation is scaling with the number of atoms. So that's what I use to allocate resources, because if you're running your calculation on the national, let's say in the past I used to use the NESC. So NESC is the National Energy Research Supercomputing Center. Now, this is one of the biggest supercomputer in the US. So at any given point in time, NESC, so N-E-R, yeah. NESC.
Oh yeah, that one.
Yes, there.
Okay.
Wow.
So in the past, this resource, at any given time, there are between 4,000 to 5,000 users that are submitting calculations, right?
Yeah.
So think about it. Sometimes it depends on the time of the year. You can submit a job and it stays on the queue for 2 weeks.
Oh my gosh.
Damn.
Right?
Wow.
And then it's going to run, and then you realize that maybe you forgot to allocate something, you didn't allocate the right time, and so on. That's why right off the bat we do our benchmark, so we have an idea that, okay, if this is the system, I know that I can optimize this system within this amount of time. So that helps me to when I'm asking for resources.
That's a smart idea, because I don't typically. I have done some estimates, right? But typically,
It's trial and error.
yeah. And so, and then also a lot of what I've been trying to work on is looking at the different ways we can accelerate a lot of these simulations using GPUs, and there is a lot of research out there, but it's not on every simulation out there.
Yes.
But I'm even wondering, like with AI and agents, right, if we can possibly just have them work on the different simulations, working on speeding them up, without breaking the physics, of course.
Right.
Because, a lot of it comes down to computation, the time it takes, right?
Yes, yeah.
I mean, it's nice that we have Buddy, right? But also at the same time, and also we just got GPUs on there, so
Okay.
that definitely helps. But yeah, there is this issue with like, all right, in order to be able to sort of understand the physics more,
Yes.
we need to wait for these simulations
We need to
and
wait for these simulations to run to completion. Yeah.
So quantum computers, I mean, it would make sense, right? Because whenever people look up like what's the application of quantum computers, it's either Shor's like the RSA encryption,
Yes.
or it's quantum chemistry simulations,
Right.
right? So you're more leaning towards quantum chemistry
I'm
side.
leaning more towards, because that's my area. So I've spent almost the past 20 years working on electronic structure. So that's my area of, I could say, my area of concentration. And I've seen how it has evolved. So if you go on Google, type in John, and then Purdue, P-E-R-D-E-W, yeah, John Purdue.
ooh, okay,
And then you're going to go on his Google Scholar profile.
okay.
I want to show you something that is very interesting about this guy.
Shout out to this guy.
Yeah, for sure.
And click on citations. So cited by,
Right here.
yes.
Just click
yeah.
on that or click on this.
Oh, let's see.
No, over there, view all. So
View all, yeah, view all.
okay.
Exactly.
Oh wow.
So this is one of the most cited physicists currently living, and you can see what is happening right there.
It's increasing.
Yeah. So he came up with this. So there is the method that we use to solve this, to calculate how electrons are distributed within more atoms, molecules, and crystals, and so on. The equation is there. The physics is there, right? But the equations are so complicated that you cannot solve. So there was a physicist called John Korn. So he came up with this idea about using density function now. So instead of looking at 100 electrons at any given time, I can pick one electron at a time, and then if I can represent the rest of the 99 electrons with some effective potential. So instead of solving for 100 electrons, then I reduce the problem
It's
to
like
just one electron.
It's like an effective field theory.
Something like that.
So
yeah.
instead of like it's like fluid simulations, you don't put every atom.
You don't
you
put
put
every
a
atom.
field vector.
Exactly. Yeah.
I see.
So with this idea, the problem became something that you can at least manage to solve. Again, it's still an approximation, but you can see that this guy was able to take that idea and build some kind of like an algorithm that can implement it. And ever since that time, electronic structure became something that everyone can do, right? So
Everyone that can compute.
and you can see what is going on in terms of research. So now chemistry, material science, physics, everyone that is studying some kind of materials, you know how to run you can simulate it easily because of this, and you can see the effect.
Yeah.
So just in 2025, his work got cited 41,000 times. That was just in 2025.
Wow,
Yeah, it's
that's
insane.
insane.
And you can come back to this graph after 10 years, right? I would say that is the trend.
It's still
keeps
rising
It's just going to go exponentially.
because it's a method that everyone's using.
It's a method that everyone is using for every kind of thing, for chemical reactions, catalysis, drug design, and everything. And now, when quantum computers, so with AI, right? AI, data science, quantum system, and so on, we're getting better in terms of approximating that density of electrons. It's called the density field, that density, right? So you can use machine learnings to kind of like learn. So now the DFT, the process of electronic structure is getting to the point where we can achieve chemical accuracy. So chemical accuracy means that my simulation, right? So what I get from simulation matches experimental results to within, I think they say within 1 million electron volt or something. So
Wow.
because of this, so it means that you're actually getting to the point where the simulations are almost capable of reproducing like
Exact
Real world
solutions.
problem.
Yeah.
Wow. So basically, in a weird way, he's the founder of DFT.
He's not the founder of DFT. So the founder
just
of
contributed.
DFT, you can type his name. It's Walter Kohn. So W Walter Kohn Kohn. Yeah. So this guy was a physicist who he won the Nobel Prize in chemistry. So he was one that actually invented the idea of the density functional theory, which is a very smart way to kind of like because
Walter Kohn.
electrons, right? Naturally, electrons have a charge. So if you put two electrons together, there is going to be some force of maybe repulsive forces and so on. So I think if let's say if I want to compare that to the solar system, right? So now, if I look at the 8 planets in the solar system, so I have, let's say, Mercury, Venus, Earth, and so on, and things like that. Now, if I want to focus just on the dynamics of the Earth, right? Obviously, you have interactions between, let's say, gravitational forces between the Earth and the Sun and so on. But the Earth is also interacting with the other planets because these are all objects that have a mass and so on. But what I'm saying is that if there is a way that, because the problem gets really complicated if I need to introduce, like, for example,
Many body systems.
body systems. So Earth is interacting with Sun, interacting with Mercury, interacting with this. It's a very complicated problem. But instead of saying that the Earth is interacting with the Sun and 7 other planets, I can reduce everything to the Earth interacting with some kind of effective system that contains the Sun and the remaining 7 planets. So that's called the effective field theory. So with that, I take a complicated system. Because if you want to simulate the solar system, right, let's say if you put the Sun at rest, and then at any given point in time, you want to study in real time how all the remaining planets are moving, right? So you're thinking about 8 planets. Now, if we assume that each planet is moving in a plane, so that's X and Y, so that's 2 degrees of freedom. So 2 degrees of freedom times 8, that's 16. So you need to solve for 16 coordinates, right? So it means that you need to know the XY for the Sun, for the Earth, XY for the Moon, and all these things in real time, right? But you can use some approximation. So for example, because 99.8% of the mass of the solar system is contained in the Sun, right? So that tells you that the interplanet interactions are very, very weak. So you can consider those as perturbations. So it means that in terms of like a Taylor series expansion, those terms are very small. So you can start to introduce them using perturbation theory. So you start with the main contribution, then you can start to introduce small contributions. So that's what this guy came up with. So
Interesting.
Wow.
I have all these electrons within a material, and it's very complicated to start to, how do you even start to describe maybe something just as simple as a helium atom, right? So there are 2 electrons there, and those 2 electrons have some kind of like interaction and so on. So
And now there's a lot of sort of add-ons to DFT, right? There's so many variations of it.
there is a lot of variations, and everything comes out to how do you accurately represent that electron density? Because the electron density is the key. That's what encodes. So from the electron density, that's what tells me if some material is behaving maybe as a insulator,
So
conductor, and so on.
DFT plus U.
DFT plus U.
Can you explain that?
So the DFT plus U is used for systems that have like strong interactions. So it's called I think they said some local effects. So systems that have like strong, so again, as I said from the beginning, you have electrons in the system, and naturally these electrons are going to be interacting. Now the way I can explain this in a very, very simple way is you can always think about electrons as springs, right? So some springs are very soft. So for example, if you think about something like rubber, it's easy to stretch. Right, so you can take rubber, and with a little force, you can stretch it. But if you take something like steel, you try to stretch it with the same amount of force, it doesn't stretch as much. So there is some materials where electrons tend to be very, very strongly bound. So electron experience like very strong repulsive forces. For some other materials, the electrons, again, they want to repel, but there is something, there might be some additional, like maybe some positive charges that are trying to bind them together. So the strength of that electron-electron interaction depends on the type of materials that you're trying to simulate. So for some materials, it's very strong. And so that's when you need to introduce some new add-ons to the DFT. Because
And so, from what I understand, this is with lanthanides or like rare earth elements, where you're in the 4f electron configuration, and so these electrons are more bound to the nucleus.
Yeah. And talking about add-ons, so that's why when I train the students, so when I'm working with my students on, I tell them about how to run these DFT calculations. So we do use some like software packages. Mm-hmm. These software packages have been developed by research groups, right, over decades, over so many years. Mm-hmm. So for example, if I were to sit down and say that, okay, let me try to develop my own code, right, there is no advantage because like I cannot beat these people. These are experts that have been working on this, and these are international teams.
Yeah.
So the way this code was developed is that you have a researcher that is working maybe here in maybe in the Oklahomans, and he's been working on electronic structure, right? So he has his code that he has developed, and there's somebody in maybe Italy or Germany, they've also been working. So these are codes that came from research groups. All right.
Yeah.
So research groups that were interested in these open source projects, they contributed their code, and somebody took all of that and make it into a package, into some a suite of softwares that you can use for electronic structure. So this has been developed over decades, over so many years, and now when we have that code. Actually, we have a code which is Quantum Expresso that is installed on Buddy. Now, because this is open source, you can have access to the source code. But again, these are very, very complicated software, so we usually do not really mess.
Hello, space travelers. Want to look sharp while bending space-time? We've got brand new Physics Society t-shirts. The clean graphic tee is just $20, and if you want to drop some Einstein-level wisdom on the back with this quote, "I have no special talents, I am only passionately curious," that one's only $25. Rep your curiosity, rep the cosmos, and support the Physics Society. Grab yours today before entropy takes over.
With the source code, right? But what we do is that we do a lot of we call it parameter optimization. So it means that if I'm trying to model a system like, let's say, graphene, which is made up of carbon atoms, it's not the same as modeling a system that is made up of silicon. Just because in graphene, the fundamental atoms or the building blocks are carbon atoms, right? In silicon, the building blocks are silicon atoms. So carbon atom and silicon atoms are not the same. So I cannot just take the same input file that I use for my graphene and just change the carbon to silicon now. So the code works using parameters. So it means that the first thing that I need to do. So I had a student that he's now at OU doing his PhD, and when he was working with me, we spent almost the first 6 months just doing all this try and error, plotting different types of graphs to see what kind of parameters can actually reproduce the type of features that I'm looking for, because you cannot just do the DFT calculation blindly, right? Before you start to work on the DFT calculation, there must be some experimental data. So for example, I can give you one example.
There has to be?
There has to be. There has to be.
So is it like you use data that's already been proven?
Now there is some calculations that you can just come up with some hypothetical material, right? There's been some work that people just hypothesize, and say, okay, maybe it seems like this material could be a stable, but it's not a material that is existing.
I
see.
But in our case, when we're studying this titanium carbide material, right, it turns out that there is experimental data about the bond length, so the bond distance between titanium and carbon atom. is known.
Okay.
So because we know that number,
Oh, okay.
we can use it to benchmark our DFT calculation. So it means that as I'm tuning these parameters, right? If my set of parameters do not reproduce that bond length
Yeah.
to within maybe less than 1%, actually, if you go on Google, so if you type my name on Google, so type Benjamin Tayo.
You want to go to your Google
To my
Scholar?
Google Scholar, right? Yeah. And then let's look at that. If you scroll down, let's look at that article on adsorption of Okay, and then you click on that reference right there.
This one?
Yes.
Yeah.
Okay. If you can scroll down,
Yeah, let's go to the
you
PDF.
can go to the PDF.
Might be a little bit easier
Yeah.
if it loads. Okay, let's just go here till it loads.
Yeah, I want to make reference to that table where it has those like.
Oh, yeah, there.
This one right here?
If you scroll down a little bit, let me see. Yeah, up.
Oh,
Then
okay,
this
this
table, right? Yeah.
Okay.
So if you look at the bond length, and then you can see the approximation. So we tested different. Again, this PBE and these are just like add-ons, as you said.
Which one's the approximate?
So these are add-ons. So there were so many that we
Okay.
tried, but we focused on these two.
So all these are approximations. Is that what you're saying?
No, these are like the values that
Measured.
are consistent with experiment.
Oh, okay.
And we found these two methods, the PBE and the PBE plus VW add-ons,
Okay.
to be the best set of add-ons that gave me the right bond-to-bond length between the titanium atom and the carbon atom.
Okay.
So we decided to narrow it down to these two particular add-ons.
Okay.
Yeah. So you can see
Interesting.
that the two add-ons are pretty consistent in terms of like the bond length. So
Yeah, very close to each
pretty
other.
Consistent, yeah.
So so which one is the true value? Is the true value in this table?
If you go, I think we cited, if you scroll to somewhere, it's cited somewhere in those references. So you see where it says the geometric parameters are consistent with reported values. So those,
Okay.
So I cited Article 28 and 29. So those are experimental.
I see.
Okay. I
Wow,
see.
that's cool. That's cool.
Experimental articles.
Okay.
Yeah.
Yeah. Okay.
Okay,
nice.
that's good. That's good. Wow.
Interesting. So, was this? Did you try a bunch of different methods, and this is just what you found?
spent over 6 months. Actually, by the time that my student was just getting to the point where, like, we were very confident,
Yeah.
that was when he was about to graduate.
Oh,
So that was a
darn.
major problem. because
Yeah.
You train someone, and then they are getting to the point where they can start to make meaningful contributions.
Yeah, and especially going to graduate school, you really, if you wanted to go and do research,
Right.
You're, hoping you have a publication to help you get into another research lab, or is he working in a lab over
He's
there?
working the same. He's still working on this, like
Okay.
computational.
Oh, so he's still at OU?
He's at OU, yeah.
Okay.
So hopefully, with the plan of the R2 by 32,
Yeah.
I think this will be very helpful because I would really love to have a student that can be part of my group for a pretty much long time, because the first
Well, for one, you just you lose a lot of information.
lose a lot of information because to get to speed usually takes
months of training.
It takes months of training.
Yeah.
Again, it depends on the approach that you're using. If you're doing experiment, the learning curve is not as bad because it's hands-on, right? You just go to the lab and you start to touch things, and then you know how to use those equipment. But theory is different because you need to learn, like, so for example, if you really want to participate in this research, you need, like, the courses that can set you up for success is so you need solid state physics.
And we don't have
unfortunately we have it
We
in
have
the
solid state
books, but
devices.
we have solid state devices, right? Yeah, so that's close to solid state physics. Yeah, but you need to learn about like crystal systems,
band gaps and
things
Material
like that.
material science.
Yeah, fundamentals of material science. And then you also need to learn quantum to be able to understand the language, right? Because
But I'll be honest,
Yeah.
like, you know, for me, I started doing research before I had those classes.
Right.
And, you know, thankfully I had a great advisor like Dr. Lamachani,
Yes.
Tej, and, you know, he's really good at teaching those things
Right.
in a simplistic way. And so, you know, I don't know. Do you think it is necessary to do research and have to have those things, or do you think
You can,
Yeah.
Do you think we can learn along the way? is
You
what
can
I'm
learn
saying.
along the
Yeah.
way if you're curious enough, and so that's why I, as the as the advisor, so I usually have these like research meetings. So research meetings come in two types. So one is like a group meeting where we meet in our group, and then we have students take turns and give presentations about updates and things like that. But I also have my one-on-one meeting with my students, right? And if you've been to my office, you notice that I have my whiteboard and things like.
Yeah.
So I use those
Just
one-on-one
always
meetings.
filled.
I use one-on-one meetings to teach the basics. So you don't need. Now AI and data science has like accelerated. You know, it has really created an advantage, because in the past, right? Suppose that you want to write an input script, like an input file, to tell Quantum Expresso about what kind of crystal system that you're trying to simulate, and you know what kind of calculations that you're interested in. In the past, the starting point would be to go. So if you go on on Google right there, and let's click on Quantum Expresso.
Yep.
So if you go on the Quantum Expresso website, yeah, right there. And then we're going to click on, there should be somewhere where it says users, right? Under users, click on documentation right there.
Okay.
Yeah. Then I want to go on, if you scroll down where it says the PW, like the first bullet point right there, does
okay.
it show anything?
Plane wave, self-consistent. No.
Okay, it's not highlighted now. Let's see.
PW com, ballistic conductance.
If you scroll up again, let me
Yeah.
see what we have right there.
Show documentation.
Click on that HTML
Okay.
where it says the general documentation. Right. Okay. So if you scroll down, no, let's go back. Let's go back. I don't think that's what I'm looking for. So it should be. Click on that road map on the left corner.
yeah.
Let me see what it says. It's supposed to be under documentation.
But it's not there.
Okay, yeah, input data description right there.
Okay.
And then click on, you see the first bullet point, and then click on that pw.x right there. Yeah.
Okay.
So this is like the pw.x is like the standard calculation, which is just like getting the basic electronic structure, right? And you can see that the input file is very complicated. It has all these things that you need to
Wow.
to input,
Wow.
right?
Yeah.
And so this was my go-to point. So I always refer the students to this site, and but you can see that this is very, very complicated.
I would get lost here. Yeah. I see.
Jeez.
Yeah. So it's
But with machine learning, with AI,
yeah.
you can generate something like a starting point.
You could even put this documentation in there and say, "Hey, help me understand this." So you know the learning curve hopefully is a little bit shorter, right? Because I mean, I don't know, because I go back and forth and thinking, okay, well, your first semester maybe you should get involved in research. But then, you know, I don't know. Like, what are your ideas? Like,
I would say start as soon as possible. I do have students that are like in their freshmen,
okay.
and I tell the students that if you have the curiosity, right, if you are willing, every student can contribute something. You don't need. And for example, there was a student, she graduated now, but she was in my group. And I remember when she when she was a freshman, right, when she started, and she joined my group, at that point, no background in calculus, no background in physics 1 and so on. But in molecular dynamics, right, we need to simulate maybe almost like a chemical system, like a solution, right? So it means that you have like some water, you have some electrolyte, you have some solute, some solvent, and things like that. And so in molecular dynamics, we have these different models of how we represent water. And so what she was doing is to study these different models, right? So in trying to do that, you're looking at some basic stuff related to the geometry of the water molecules and just calculating some distance. So that's all just like trigonometry. So looking at water molecule as a V shape, right? And then breaking it into some X and Y using cosine and sine. And then from there you can extract information like dipole moments and so on. So just that is part of, like, you are doing something, right? You're trying to learn something, but you are not really like, so everyone can contribute something. So I meet you where you are, and I assign you a project that is kind of like compatible with your background. And then you simply walk your way up.
Okay, so let's say a student comes up to you right now, or like a bunch of students, right?
Yeah.
They ask you for a starting point, a general starting point of what they should tinker, right? What do you think they should tinker if they plan to get into this kind of like computational material science and all that? So solid state physics, where should they start? Let's say they are a freshman or a sophomore.
Yeah. So again,
Like just a general guideline. It doesn't have to be specific. Yeah.
Some basic skills like
Python maybe.
Generally, it always comes down to having a good analytical background, like some good background. I think math is always like the main, like the main foundation that you need, right? If you understand your math very well, the physics comes in, because physics is really math, right? So most people struggle with physics because of math. So I always say that for me to be successful in physics or maybe engineering, the starting point should be a good background in math, because how are you going to understand things like, let's say, band structure, or if you're talking about quantum information systems, all those linear algebras and unitary transformations and so on. So math for me is the key. And I feel like I can testify to that, because with my strong background in math, for me, like when I'm trying to learn something new in physics, it comes like pretty fast. Like I can pick something, and like if I pick something, I just need a limited amount of time to understand the equation.
Because math is the language, right?
Because math is the language, and I think my background in math is pretty good, because math was my first love.
Oh, wow.
So math was really like what I like, what I enjoy. I didn't really like physics, but math is the thing that I'm really like. I love it. So sometimes I really consider myself as a mathematician. I love the approach, because math is about first principles. In physics, we try to hide. I mean, like, I can just give my students maybe some metrics. It could be something like a 3x3 matrix, and then I can say, can you calculate eigenvalues or something? But we're skipping a lot of steps, right? So first, mathematicians will take that matrix and try to say, okay, can I prove that this matrix has the right properties that would make the eigenvalues to be real or complex? So they always do things from the first principle, which I feel like that's a natural way to approach any problem.
Yeah.
First principle.
So
Write that down.
So with your quantum mechanics slash quantum computing course, right? So what's like the main through line? Are you teaching a lot of the algorithms, and what are like? Is there just one main algorithm that you're teaching? Is there a ton of algorithms? Like what does a test look like?
So the test looks like so the first part of the course was just to introduce do a little bit of review on linear algebra, so matrices, eigenvalues, and stuff like that. Then we introduced this idea of the block sphere, which is like a general qubit system. Then from there, we introduced basic quantum circuit, because is the idea of the course was to introduce students to help them to build that background. That can help them develop the quantum, like to think about like logical systems. So quantum logic, something so to speak. So qubits, and then we did like some basic quantum circuits. So basic quantum circuits are things like, so maybe if you think about in digital systems, like let's say the NOT gate, right? So the NOT gate, what it does is that it takes some input and then
Flips it.
it flips it. So you can come up with some truth table on how it does that and so on. So the quantum circuits are doing something similar, but the difference here is that what really transforms the input into the output is just some matrix multiplication. So you start with some input, which is maybe a 2x1 matrix, and then the quantum circuit itself is represented by some effective, matrix. And then the process of taking the input into the output is just to multiply that input vector with the matrix to get the output. So we did a little bit of this, and then now that we have some background, we're beginning to explore how do we go now from, let's say, basic quantum gates into quantum circuits. So to give you an analogy, if you think about let's say in basic electrical science, right, you have maybe simple circuit elements like your power supply, your DC power supply, you have your resistor, you have your capacitor, and you have your inductor, right? These are the building blocks, these are the elements. Now, if you want to make a complicated circuit, you can have a complicated circuit that have, let's say, millions of resistors, millions of capacitors, millions of inductors, right? So you're going now into more complex systems. So that's what we're doing. So we're starting from the building blocks, like the resistors and the things that you need to put together to make complex things to work, right? So in quantum, those basic quantum gates, like the Hadamard gate, and so on, the swap gate, and so those are like the basics. Now you can put those into, like, you can start to build off of that into much more complicated circuits that can do. So right now we're just at the point where we're starting to get into some algorithms. So for example, the Shor algorithm and so on. But it's because this class, right, the first offering is almost like we're learning as we go, right? So we're trying to find like the right things that can be done within a 1 semester kind of time frame. So for now, we're trying to explore some algorithms, and again, these algorithms are not really simple, right? These are not really like just the standard.
It almost feels, from how you're talking about it, almost feels like computer science meets electrical engineering meets quantum physics.
Quantum physics meets, I would say, even computer engineering.
Yeah.
Because now the hardware is also another topic that, because my question is, I really want to understand how do you realize, how do you make a gate in the real life, like, there are from a physics point of view, there are things that you can do, like there are so many ideas. For example, in an atom, right? An atom has these energy levels, right? And if those energy levels are very close, electrons tend to kind of like be somewhere in between. So I've read some articles where they say you can make a qubit using
atoms,
just the atomic energy levels. So if you pick the right atom that has energy levels that are very close, because qubit simply means that randomness, right? Like something that is not predictable.
Yeah, because the ones I've read is like there's the 4 main types. One is photonics, you use light. So you use polarizers, resonators, and all that.
Right.
The second type is you have superconductors.
Right.
So like the Josephson junction,
Yes.
and that creates a superconductor qubit.
Right.
Because it's either the supercurrent go this way or supercurrent goes that way.
Yeah.
It's in a superposition of both, and then you have neutral atom, and an ion,
Right.
trap ion.
Right.
So
right,
these are the
right.
4 main popular methods
Yeah.
of like creating quantum.
So it sounds like maybe using a resonator might be one of the easier.
Well, allegedly, because they all have their own problems. But right now, a lot of the companies in China and even United States are investing in like trapped ion, superconducting, and photonics. So that's all of them have a lot of investment.
Yeah.
So what do you like? So the question now would be, do we try to bring the university to test all 4 approach, or
Which also kind of leads into another question, which is, are we trying to do research into this stuff? Like, did you have any thoughts on?
Long term, I would say yes, because as I said, I think we have like the ingredients, like the necessary background. So, but again, these are really. It's going to take some investment, so we need to invest in some hardware. We need to invest in clean rooms and so on,
oh yeah,
in order to really get to the point where we can start to create those like the hardware that we need, at least for simple things. But I feel like Dr. Lami Chin is a pretty good material scientist. I think we can make use of his expertise. And then I can come in from the point of view of, like good theoretical background, and there was some input from students. But all these things, I feel like we should be able to like have some research projects in this direction, because these are like exciting
avenues, right?
exciting avenues. And if you really think about how the field of computing is evolving,
It's
I
rapid.
think there is a lot of interest in this quantum. That's something that I myself, right? So I'm thinking, because I submitted my my proposal to renew my grant, right?
Yeah, which I would love if you would
And
talk a little bit about later.
I'm waiting for the outcome, which I think I should be able to get some feedback by the summer. But I'm also thinking about taking like almost a 360 degrees or maybe 180 degrees, like a U-turn. And because for me, I'm a dynamic person. I don't like. I'm not a static person. I like to explore. That's why when I go to conferences, I always like. I go around and listen. I always listen to a lot of student presentations, because for me, I want to learn, because I don't know, right? I want to keep learning, exploring new things, and so on. So I have different ideas, but I really want to make a turn. Now, for the project that we have ongoing right now, I think it's a very, very interesting project, because it's not just about biosensing, but it's also about anything that is related to the interaction between a molecule and a surface. So you can use it for any kind of application, like gas sensors and so on. So for example, you can build some kind of devices to sense. I read an article where they said that, so basically they took our research, the same research, right? But we have our sensing surface, right? And we're putting these molecules on top of the surface to see how the molecule can bind to that surface, right? And because different molecules have different chemical properties and so on, so the degree or maybe the uniqueness of the interaction between the molecule and the surface can give me some kind of fingerprints that I can use as signatures to identify these molecules. So I was reading an article where they did the same thing. So we are using these DNA molecules, but for them they use the same material, the same substrate material, but they said that there is a molecule, I forgot the name of that molecule. There is a molecule that people that have like lung cancer, right, when they...
A biomarker?
There is some molecule that when they're breathing, right, when they expel, when they inhale and exhale air, that molecule is contained. So people that have lung cancer, right, they exhale this air that has a molecule. I need to look at the reference, the name. But that molecule, right, so what they're claiming is that if they can build some kind of nano device, right, how can you distinguish that molecule from air? So air is made up of, carbon dioxide, some water vapor, and something like that. So basically what they were doing is using the same approach, but just applying it to a completely different.
Interesting. Yeah.
So the hope is that they can use this for some kind of like lung cancer, early diagnosis or something.
Yeah, well, that makes a whole lot of sense, right? Because I've heard that, yeah, you can just tell a lot of things by the smell of someone's breath.
Right. Yeah.
So volatile organic compounds.
Yes, something like that. Right. Yeah. And there is one
Volatile organic compounds.
Hey.
Yeah.
And there is one specific. I can look up some.
Aldehydes, ketones.
I'll look up some
ketones,
like
hey.
the reference.
Isoprene, benzene.
It's pretty interesting. So the main problem now is still investment. So we would need investment to get new space, a clean room for like quantum, hopefully future quantum research.
Right.
And I would think, in my opinion, I'm a bit biased, but I think photonic quantum computing should be what we focus on in UCO.
I mean,
We don't need all that cooling stuff. And all.
Okay.
We
Yeah,
just
that's
need
a good. I mean, we need to all discuss some kind of like feasibility, and I think this is where Dr. Page can come in
and help out with
some because I think we need to apply to some kind of funding as well.
yeah.
I think there are so many. I think there is some like federal funding opportunities where you can apply for some kind of instrumentation. Like if you're trying to develop this idea, right? It's almost like a kind of like a seed grant where they give you some investment for you to like build the resources that you need. And I think Dr. Tage can really. I mean, myself and Dr. Tage, we have. I mean, we've been bouncing off ideas. I think there is just so many good ideas that one can explore, especially like right now. I think UCO is gaining a lot of strength in material sciences. So I've been going around and
We're gonna need a bigger lab.
another STEM building.
Something that I feel like I'm getting better at is to build research teams. Yeah, so I try to go around. Like right now, there is a professor in chemistry. He just Dr. Osinde. He's originally from Kenya. But he's an organic chemist, so it means that he can synthesize any kind of thing. So, and then in chemistry we also have Dr. Kern, who is a physical chemist, right? So if you think about it, physical chemistry, there is a lot of overlap. Physical chemistry, material science, right? Then in engineering we have Dr. Tage. So I'm trying to put together some kind of team.
Yeah.
That if we have that team together, I think the sky is the limit because we can pretty much do anything. So we bring in some expertise from different areas, put it together, that we should be able to tackle some, So the way it works is that first it has to go through a proposal. So we need to form a team, write a research proposal, apply for a grant, right? And then once you have some research funding, this is where you can really start doing the research.
Yeah. So I guess to go back to what Albert was asking, is there like a specific circuit that you're looking at, a specific application, or
So is it one of the main few projects, for example, like a VOC detection system for like when you breathe, or like what specifically are we looking
at this point in time right now so if you think about the proposal that we just like resubmitted, that problem is to try to solve. That proposal is to try to solve some of the ongoing problems with DNA sequencing. And one of the problems is the noise in the data. So the data is pretty much like, so you have these ionic current signals, and they are very, very noisy. So maybe let's go on Google. So type maybe MOS2, yes, and then type nanopore like PORE,
Pure. Oh, okay.
And then let's say ionic signal. And then I want to see if we can find something that has some images, right? Let's see something. Right, you see this one right here?
This one?
No, bottom. Underneath, yeah, this.
Okay.
Yeah.
Let's see if we can get it bigger.
So that problem, so this is actually this group.
Oh, okay, yeah. I've seen,
If you went to my
Yeah.
students' presentation, we have an.
Yeah.
So I got data from this group. So this is a group from Europe. Dr. Redenovic, she is a world expert in, in making these nanopores in MOS2. So MOS2 is a crystal. So she is making these nanopores in her lab,
Yeah.
and they're actually collecting the translocation data in real time.
Wow. Yeah.
So what they do is that they take a segment of the DNA that is
nucleotide.
already. So they take some like experimental DNA that they already know what the sequence of that DNA is, and then they run this like experiment to see if they can reproduce. So it's a well-known DNA, so they already know what the sequence is.
Okay.
And this is what they got from their experiment. You can see that if the system was perfect, you would not have any areas of overlap, right? So if you look at it very well, you can see that there are some areas where,
Some overlap here. Yeah.
So some areas where the blue is getting to the red, the green is getting to the orange. So all those areas where the blue, where you have those overlaps, right? Those are called random effects. So those are not real effects. So random effects means that in a real solution, right? In a real solution, because the DNA has a very complicated structure, it's not just like a line, it's not a linear structure, it's some complicated three-dimensional helical structure or something. So when you use that in a real experiment, it's possible that as the DNA is trying to go through that pore,
It's like winding around.
it's winding around, so multiple nucleotides are interacting with the pore at any given time, right? So that can create some noise in the signal. So there are so many approaches that, and this is really like one of the limiting. So the method seems to work well, but you have this limiting effect that there is a lot of noise in the data. So there are two ways that you can solve it.
Yeah.
You can solve it using some kind of machine learning where,
Like denoising.
you can denoise, which is what my student is doing.
Yeah.
You can take the real experimental data in real time. Maybe if there is a way that you can export it to some cloud, then in real time, you feed that data into some machine learning model for it to filter so you can remove those. Again, when you filter the data, you want to do it very smartly because
You don't want to lose information.
you don't want to lose information. So I would say it should be a very small percentage of the data, like maybe 5%, 10%, because machine learning depends on data, right? The more data that you feed, the better. If you filter and you throw away a lot of your data, you are reducing the size of your data. And if you are reducing the size of your data, your machine learning
Reducing
model is going to
precision,
suffer.
accuracy. Yeah.
So we got this data from this group, and actually one of my students, and this is a student also that, when he joined, he didn't have any background on machine learning and data science, but he's been doing some really good work, so applying some different statistical...
Is that Jace?
It's Jace,
Yeah.
Yeah, it's Jace.
Yeah, I'm actually looking to get Jace on here so he can
Yes.
maybe talk a little bit about it.
It would be really good, yeah.
Yes.
So there are two approaches where you can use this statistical, so you are adding statistical methods into the experimental, because the experimental prediction itself is not very reliable, right? So you need something in order to get it to the point where you can really say that this is chemical accuracy. So with that, you can say that there is a lot of error. I don't even think that you can even get maybe less than 75% in terms of the accuracy.
Wow.
Interesting.
Yeah. So those are the two pathways. So in our proposal, we're proposing that we want to solve this problem using a combined machine learning, advanced statistics. But we also want to try to see if we can explore new materials. So MOS2 seems like it's a good material to use, but the field of material science is evolving. So who knows, tomorrow there might be a new material that tends to do better in terms of like stacking. So DNA can actually bind a little bit with that MOS2 with the pore. It can bind with it. So if we can find a material where that binding energy could be less, so it means that when the DNA is going through, it just like zips through. It doesn't really like stay. So how long the DNA stays within that pore is calculated using that dwell time right there.
Okay.
Oh.
And the dwell
see.
time, from what we've done in our calculation, is the source of the noise. If you look at that figure right there, look at the horizontal axis and look at the vertical axis. You can see that the horizontal axis has the greatest spread. Right? Look at the red values.
Yes.
Yeah, 0.2 to 2, or 0.02 to 2, and then 0.2 to 1.2.
Yeah.
Or 0.4. There's that outlier all the way up there for some reason.
Right. Yeah. So we calculated the uncertainty in the data, and for the current. Excuse me.
You're fine.
Forgot to put this thing on mute. So for the current, the uncertainty in the current values are, 5 to maybe 10% or something.
So do you think there's like a way to predict for this type of property that you're looking for? I mean, like for magnetism, we can use like structural parameters to try to predict for.
As a matter of fact, that when Dr. Tage came in, he actually suggested that in addition to using this traditional sensing, we can also explore some magnetic effects, like because it's almost like a crime scene. The way we're solving this problem is a crime scene.
Yeah.
So, for example, let's say, so tomorrow I go to let's say I go to the police station and I'm making some claims that my car was stolen.
Yeah.
Right? So just that information that my car was stolen, it doesn't help them that much, right? But now if I could say my car was stolen on this date, on the 2nd of April 2026, that's one data point. Then the next step was maybe what type of car were you driving? So if I can tell them that my car was stolen on the 2nd of April and this car was a Toyota, that's one data point.
Yeah.
But now there are so many models of Toyotas. Now, if I can go to the next level and I say this was a Toyota Camry, that's also one data point.
So narrowing it down.
I'm narrowing it down. And then I can even say this was a 2020 model, and then it was blue. So each data point that you add gives you more ability to kind of like narrow down to the. And that's something that I feel like in this model, they only focus on 2 parameters, right?
Yeah.
So it really doesn't narrow it down enough.
It doesn't narrow it down. So basically, we've been able to engineer 2 more features just based on this data.
Okay.
So we calculated the charge. And what is the charge? So the way this method works is that you have a solution and then you put salt. So salt is sodium chloride.
Oh, the polarity of the molecule?
The polarity of the molecule. But we're actually calculating the current here is called ionic current, which is like the number of sodium ions, because the sodium ion carries a positive charge. So you're just counting the number of sodium ions that are going through that pore in real time.
So let's say, like adenine, for example,
Yes.
it couples to a lot of like, because let's say it's slightly polar, like slightly electronegative.
Yes.
So it attracts more sodium.
Exactly.
And it goes through with the sodium.
Right.
So that's like a marker for you.
You can correlate it that way.
I see. That's wow.
So we're trying to extract that information from, and the way that gives us some kind of advantage, because like we don't need any extra measurement. We're just taking this data, the current and the time, and we're calculating the area under the signal, because the area under the current time is like current times time.
Yeah.
Which gives you charge.
So you can just use a saline solution and put some DNA in there, and you can use it to start detecting.
Right.
Wow.
Yeah.
Theoretically.
Yeah. So those are, and then in the future also we're thinking about this additional, like some magnetic effects or something. I think Dr. Tej has some really good ideas about using some kind of even optical sensing like Raman spectroscopy. So there are so many ideas. So we're going to team up with OU. So OU has a, I think they have like a Raman spectrometer.
Okay, yeah.
So we're going to team up with them and see some things that we can do. So if this gets funded, that's the next step. So the next step is to go now towards more hands-on. Because everything that we've done in the past is just like, DFT simulations to try to predict what is possible. Now that we have some data, we have some ideas about things that can work better than other things and so on.
Yeah.
We want to start with doing some really simple things like how can we even do something so we can get, and in the proposal, which is, again, I don't want to be too confident, but I'm kind of keeping my positivity. I'm pretty sure that I'm being optimistic that we might.
Yeah.
Because this time around, we're including, when I had submitted the proposal in the very first cycle, one of the main questions that came back was, okay, your idea seems really good in terms of like the theory and the math and everything, but how are you going to test this in the real life? Like, how are you going to verify that this works, right? You can show some theory and things like that. But one of the limitations was most of the reviewers were asking me, how are you going to do this in practice? Or if you cannot do it, can you find some experimental collaborators that they can do the lab, they can do the experiment? So I had to contact some people that provided like some kind of like letters of support that, hopefully if some good ideas come up from the theory, they can potentially like try to see if they can get this done in the lab and so on. But thankfully now we have a really good experimental team at UCO, right? So as I said, chemistry, School of Engineering. So at this point, we have the expertise that we can start to try some really simple, we'll start from something that is simple, maybe just graphene, and then we'll start to move on. Like we learn from graphene, from there we start to explore new things, and so that's the pathway. So the pathway is to go towards more the experimental application.
But so, do you have any thoughts on what problem you would want to solve in quantum computing?
So quantum computing,
or at least a general area of
right. Quantum. I think what stands to my mind is really this electronic structure, like quantum chemistry, like to really see the advantage. Because right now there is a lot of limitations. So you can only do, you can solve. So even with all the supercomputers that we have, right, DFT, so this electronic structure calculation is still not realistic in the sense that you cannot simulate real systems. You can only simulate like very small, I think to the best of my knowledge, maybe under 1,000 atoms. So systems that have under 1,000 atoms. That's almost nothing, right? Because, for example, if I want to simulate, let's say, maybe just a small segment of the DNA, which is the genome, like one gene, right? That could almost be like 1,000 nucleotides.
Yep.
Right? And one nucleotide probably has, let's say, 20 to 30 atoms. So that's almost like 30. That's just the DNA alone. That's about 30,000 atoms. And then you're looking at the solution that has a water molecule and so on and everything. So you cannot use DFT in practical problems. Just because the problem is too complicated, you cannot. So I want to see, for me, I want to really see where, if these quantum computers can really get to the point where we can start to apply DFT to real world systems. Like, for example, you can even start from systems that have more atoms to very even simple organisms. Like you can simulate things like, bacteria, viruses, and so on.
So like quantum simulators, right?
Quantum simulators, right, yeah.
QDFT.
Yeah, but real, using real quantum computers.
Yeah, so that's really one of the problems that I really want to see. how, how this feel.
So it would be more trying to use sort of a quantum computing platform to try to solve some problem instead of trying to sort of build and do research on how to solve like some type of circuit problem in quantum computing.
Right. Yeah. So this is more like application. So suppose that we already have a quantum computer that is functional, right? How can I take this problem of quantum chemistry that I've been solving? How can I? And it's going to be a game changer because now we need to write new software that you can actually use in this, quantum platform.
Yeah.
And the plan is that the software must produce an advantage, right? Because if you're not getting any advantage, like is the quantum system, is it helping me to solve my problem at maybe T over 10 times less or something? If I'm not getting an advantage, then what's the point? Right?
Yeah, and there's this whole idea that AI is going to take a bunch of jobs, and people say, oh, software engineering is dead, and all of this, but our compute hardware is going to just get more complex, and we're still going to need software engineers to figure out the algorithms to code on those new types of hardware. So, I think we're going to need more software engineers, honestly.
We need more software engineers.
Yeah.
I agree.
So, I don't want to keep you here too long. What time?
Probably maybe another 20 minutes or so.
Okay. Then I want to. There was a question on the Discord that somebody had asked. I think it was Anjali, and I wanted to ask you this question. So let's see here. So one of my favorite questions that she asked is, this isn't her specific question, but it's related to her question, right? So I know you have a son, and I'm sure you have a bunch of family members also, right? Do you try to teach them the things that you teach in class, or do you do a lot of that, or?
Well,
because
it's kind of hard because in my family, I'm the only one that is more into physical science.
Okay.
My siblings are mostly into, I don't know, liberal arts or something, but like history and geography and so on. Now, each time that I have a new publication, I would, just share with them for them to just but they don't have that background. So I can do stuff with them. I explain stuff to them, but in a very non-technical way. So, yeah. But my brothers in particular are very excited about they're very curious about learning.
Okay.
Yeah.
So are you hoping that your son's going to become a physicist as well, or?
My son. So my dream is, how LeBron James plays in the NBA.
Yeah.
So my dream is that hopefully I can co-author with his son.
Yeah, that would be awesome.
That's my goal. That's my dream.
That would be awesome. Yeah. So, okay, let's see here. Another question. Let's see here. So, yeah. So she asked, how do you treat new stuff you hear about, right? So you seem a very curious person, and I'm sure you're taking in a bunch of input. And so where do you hear a lot of these new ideas? And let's see here. Yeah. Where do you hear all these ideas, and do you keep a log of them? Do you dive straight into them? Do you wait for a certain time in the year to, how do you?
Do you have a specific area you look for, like a specific website or something that you look for this new information?
Mm-hmm.
So I've gotten a little bit lazy, but in the past I used to read. Make it a goal to browse at least maybe 20 to 30 articles every day. And the website is called Archive, A-R.
Oh, okay, yeah.
Oh, Archive, yeah.
So they usually post so these are papers that maybe is still under peer review and so on. So I would go, I can explore some, but I usually go, if you go under, it has to be under something. Let's say, okay, you see where it says material science or somewhere.
It's in
under
physics.
condensed matter.
Let's see here. Oh, right here?
Yes, click on that condensed matter. Let's see.
Uh-huh.
No, let's go. Oh, yeah. Scroll down.
Okay.
Let's go back.
Okay.
I know under condensed matter there should be something about like nanoscale physics.
Oh yeah, nanoscale.
Yes, right there.
Meso and nano.
Oh, right here?
Yes. Yeah. So I always, because I'm working on material, so I always go here and.
Oh, okay.
So I would browse it. So I browse it.
Uh-huh.
So these things is updated every day. So I usually go there and just like pass my eye through.
Uh-huh.
And then every now and then maybe I can download like 2 or 3. So if something really catches my interest, I can just download it. And then I have a folder. I have this folder that I have that because I like paper and pen. I'm a theoretical physicist, so I believe in writing. So I'm writing. If I'm reading, I take down some notes. So I write the title of the article, I write the date, and then I make like a 1 or 2 page summary about that article. That helps me to keep track of what I'm reading, so I can always come back. And then sometimes I read also on material science and things like that. And then also I do review, like, research articles that have been submitted for publication. So I go over those. So they usually assign some of them to me for me to review. So those are all opportunities for me to learn. Like when you're trying to review an article that has been written by someone else, it's an opportunity for you to like read the paper. So you want to give like an unbiased kind of like, assessment. So you need to read it carefully, try to understand the science. Is the science convincing enough? Are they presenting it well? What's the quality of the work? You need to judge all these different criteria. And then at the end, you need to write like some feedback, like what is your input? What is your feedback as to whether it meets the criteria for it to be published, right? Or is there some additional stuff that you're recommending? Yeah, so those are all opportunities that that I try to learn new things. But I also like to go to conferences. Because conferences, I think, each time that you go to a conference, you meet new people, you listen, and yeah. So I like the fact that academia, so the university gives you that opportunity to really like branch out and spread. It's almost like there is no limit.
Yeah.
So you can really explore a lot of. It's just that time is also a constraint.
Yeah.
Because you can have some really good ideas, but. Like right now, there are some things that, if I had the time, I could be doing some calculations as well or something, running some input calculations, but
Yeah, like so.
it's really hard. Yeah.
We talked to Dr. Waters, and she has quite a few students under her. Do you feel like you have a limit to as many students you can have under you? And
what would that limit be?
Yeah,
If you have a limit.
And the reason why I'm asking this is because, this is, what you're doing is something I'm interested in doing in the future, right? Like essentially running a small research sort of team, right? And so I'm wondering, like, like how many fields do you think you could possibly or how many like different types of projects do you think you could have even going at one time?
So as many as possible, but these projects cannot just be random, right? So it has to be, for example, since I have like a funded project, I have to make sure that for the purposes of like reporting and things like that, whatever project that I'm assigning to the student, it must be under this umbrella. Like it has to be within this area of, let's say, DNA sequencing using statistical methods, machine learning, MOS2 or 2D. So it must be within this area right here. Because that's like the funded project. So if a student is hired as a research assistant and if I'm going to be supporting them, then they have to be working on this area. So again, there are just within this is even one of the reasons why I feel like this project is very important, because it has so many components, right? You can do the DFT part side of things. You can do the statistical analysis. So you can come in with different backgrounds and you can contribute something. So so I usually I don't limit, like, who can join the group. As long as I can find something. And it doesn't matter, like I've had students from maybe computer science, computational engineering, mechanical, electrical, whatever. What you just need is to tell me, if you're interested in doing some research. And my mentoring style, I try to give you the freedom. So I give you the freedom to try to approach the problem by yourself. So I direct you, but I'm not going to be after you every day to try to put pressure on you. And so I want you to be able to learn freely out of your own motivation, right? So, and I've seen that is actually very useful. Like if you give the students the freedom, because that's what research is all about, academic freedom. So academic freedom means you should be able to explore what you're interested in. So if a student tells me that they're interested in joining the group, I assign the project to them, but I don't put any time. I mean, sometimes just for the purpose of staying organized, we usually come up with something like a research plan, and we put some benchmarks that maybe, okay, after 1 month, you should be able to get this done. So, but that's just to guide them. But I try to let them, and I think the students have been more productive when there is no restriction. So if you just let them, give them a but I always follow up with the students. So I need to track the progress. So I'm keeping up with them. I'm having these weekly group meetings with them and so on. They are giving me feedback on what they're doing, and I can track the progress, right? But at the end of the day, I also want them to be able to be free. Because if you're not free, it's not like you're doing it for me, right? I can do it myself, but again, if I do it myself, how are you learning? So that's the whole idea, is to excite them, get them to be curious, so that hopefully they can learn the skill set of being like a successful researcher.
So when do you think that we're actually going to have a PhD program, and what is that going to look like? Is it because from what I've heard, it's going to be more of like an applied engineering or something like
Applied
that?
physics or something?
Right. So everything has to start from somewhere. Even if you look at the history of the School of Engineering, right? It started as a physics department, and then over time, we created these emphasis areas and so on. So when you're applying for a PhD program, you cannot just right off the bat, you cannot create this special programs. For example, you cannot just say I'm going to be offering a PhD in electrical engineering, PhD in mechanical engineering, because such an approach would not be feasible, right? So there is some restrictions on, for example, the state of Oklahoma has it's called the RUSO, which is some kind of a governing body that,
The Board of Regents.
The Board of Regents, something like that, So if we're going to have a PhD program, there is some metrics. So for example, how many students do we plan on graduating every year? So there are some criteria. So for a university to be an R2 university, under that category of R2, there is some criteria. For example, it has to produce this number of PhDs per year. It has to receive this amount of funding in terms of, research funding.
At least 20 research doctorates per year,
Yes.
and at least 5 million in total of annual research expenditure.
Exactly,
So we would even need the students to want this as well, right? They would have to,
But so this is across the board. So the 20 to 30 is not just from the applied sciences. So right now
It's
we
the
have,
whole university.
it's the whole university. So we have a
Okay.
program now. I think there is some PhD program in
Forensics, education.
forensics, education,
Okay.
and so on. So all of this
Yeah.
has to be 20 to 30.
Okay.
So at this point, if we make it specific, we might not be able to reach that target, right? But if we say PhD in applied sciences, it means that, so right now there are 3 emphasis areas that are being promoted. Is biological science, engineering, and then computer science. So those are the 3. So now, if we have like a PhD in applied science with emphasis in biological science, PhD in applied science with emphasis in, so any student that is going to graduate from this program, we can count it as one program, right?
I see.
So at the end, but hopefully, if the program becomes successful, over time, we can start to branch off, like say, okay, now we can create a PhD program that is specific to maybe electrical engineering, physics,
see.
ME, and so on. Yeah,
Well, yeah, I even know that just within our research group, there's like 3 or 4
right.
people that would be interested if UCO had something like that. So do you have a estimate for when?
So, as you know, Dr. Lemley he's like the interim dean. So he's interviewing for this position to become the dean. And I went to his presentation, which was actually on Monday. And in his presentation, I think he gave like a pretty good vision of what he wants for, like if he becomes a dean, his vision for leading the College of Math and Science in this pathway of becoming a R2.
R2 by 32.
Yeah, so I think he's very, very supportive of research. I don't know. At this point, I think it seems like it's, from what he said, it seems like the first stage of the review was successful or something. So it has to go through some cycles of review by different. So first it starts from the College of Math and Science, and then internally, right, it goes to the provost office, and then if it gets approved there, then it goes to the RUSO, the regions, and so on. So I think he was saying that if everything works well, fall of 2027 might be when we actually officially have the first batch of students, right?
Oh, wow.
Yeah.
Wow. So that's just a year away.
Just a year away. So
That's awesome.
yeah. I mean, I could see a lot of opportunities because I know even some of our faculty members here, they might be interested in the PhD. For example, Professor Prather.
Yeah.
Because Professor Prather has a master's degree, I think he would love to have a PhD. And that might be something that he could actually juggle. So he could still be an instructor and be doing his PhD. He doesn't really...
Which is perfect.
Which is perfect,
Yeah.
So, yeah.
All right. Well, Albert, do you have any other questions or? All right. Well, I guess we should get you out of here so you're not late to your meeting.
All right.
I really appreciate it, Dr. Teo.
It's always a pleasure.
Yes, sir.
All right.
I hope to be back again.
Heck yeah.
Next time, come back and we will talk more about all those
All right.
theories.
Yeah, hopefully we'll be talking about a specific idea in quantum computing here.
Yeah, I hope that by then, we'll have some, at least, as I said, we're trying to get some of these algorithms to work. So hopefully before then, we'll try to see if there are some extra resources that I can share with you.
Yeah, for sure. And just know, just let us know if you want to come back. We would have you back on next week if you wanted to.
Yeah, you can come back anytime.
At some point also, let's have some kind of a podcast where I'm going to be the one asking the questions.
Okay.
Oh, that'll be good.
Yeah.
So that I can see things from your point of view.
Yeah, because he just got another mic.
Yeah, I did.
Yeah, he has another mic in a stand, so we can have 4 people now.
Oh.
Easier.
Yeah. So we could maybe even invite another student,
Yes.
maybe one of your
right.
students doing research with you.
Exactly.
Or 2 professors.
Or 2 professors.
Have you had Ed Musa, Dr. Musa?
No, I've thought about talking to him. about it.
He would be really good.
Yeah. Okay.
Because he would have a really good perspective on AI, especially in robotics, like robotic engineering and things like that.
I'll write that down. Because this is the first semester that I've had him as a professor. He's our mechatronics lab instructor.
All right.
And so it's been really nice getting to know him. He's a great guy and a great
He's a really,
instructor
really
for
smart
sure.
person. I mean,
Yeah.
when it comes to hardware, if you have any questions related to hardware, even in computer engineering, like
Undefeatable.
he is really good. So he would be good to have. I think he can give some really good.
Yeah, and the robotics club is pretty big here at UCO, and I know that NVIDIA has recently said that it's the year of robotics, so they're trying to build robots as fast as they can, and so I think that's also another
NVIDIA also
thing that could be building and being a lot larger here at UCO is the robotics
Research.
stuff. Yeah,
robotics research.
And also, like, even NVIDIA is investing a lot in quantum computing. So that's also an interesting thing.
Yeah.
Interesting. But yeah, just let us know when you want to get that set up, and we'll get it done.
Sounds good. Thank you so much.
Well, until
Next time.
all right. Awesome.